Good afternoon, everyone. Can you hear me? Excellent. Good. Thank you. Excellent. Okay, so a few reminders. We have quiz 5 is due before class on Wednesday. That's the quiz covering queuing theory. And hopefully I will finish that material today. And lab 2, programming assignment 2 rather, is due on Friday by midnight or by 11:59 p.m. But also to remind you though, if you turn that in by Sunday night by midnight, by 11:59 on Sunday, you won't lose any. There won't be a late penalty because the late penalty is applied per weekday or per school day. So you actually have till Sunday night to submit that without a penalty, but the due date is technically Friday. So that's lab 2. And also we need to take care of the second midterm exam. We need to get that out of the way. So I'm planning to finish the material on queuing theory today, and then we are going to switch topics in the course to topics that are more hardware oriented, low-level hardware oriented. We're going to start talking about CMOS design and noise on wires and stuff like that. So we're going to depart a little bit from the mathematical aspects of the course. So this is a good time to have the second exam, which will kind of tie up all of the mathematical parts of the material. Also, the withdrawal date is March 27th, which is a Saturday. So not this Saturday, but next Saturday. So my plan is to do the second midterm exam on Monday, a week from today, March 22nd, and that'll just cover real-time scheduling and queuing theory. The quiz 4 was actually due last Wednesday, and I haven't gone over quiz 4 yet. So I'm going to go over quiz 4 today in detail, which covers real-time scheduling. And then quiz 5 is due before class on Wednesday, so I'll go over quiz 5 on Wednesday, and then I'll spend the rest of the time on Wednesday just reviewing and answering questions. And then we might get done a little early, and you'll have some time to work on lab 2, which is due on Friday. And then we'll have exam 2 on Monday the 29th, and then on the 31st we'll start the next topic, which will be CMOS design, transistor level design. So I'm sorry for the late notice. I'll send an email out too about the exam. But this exam probably covers a little less material than the first one. So like I said, it'll just be real-time scheduling and queuing theory. So hopefully that'll be reasonable for everyone. And then you'll have from the 22nd, you'll have your exam score back on, how does that work? You get the score right after you submit it, or is it they come out the next day? I forget how that works. But in any case, you'll have your exam score by Tuesday. So by that point you will have you'll have 5 quizzes and 2 exams and 1 project, and you'll have hopefully submitted the second project, although we might not have them graded by Tuesday. But you should have quite a bit of grade. So if there's any issues and you do need to withdraw, then you'll have till the following Saturday to withdraw if need be. I hate to think that, but I know that sometimes that happens, and sometimes some people are a little bit overly ambitious and take a lot of courses and get overwhelmed. So I just want to make sure that you have that option if necessary. Although I get the sense that most people are doing well in here. Okay, so let's start out by talking about quiz 4, which I should have did last time. Okay, hold on a second. Share application. Okay, hold on 1 minute. Sorry for the delay. So Blackboard isn't seeing all of my application windows, so I'm going to have to share my whole screen here. Which is fine. Okay. Okay, so hopefully you can see that okay. Let me know if there's any, if this is getting cut off. Oh, we had a question. Will there be any new content? No, there won't be any new content on Wednesday. I'm just going to review for the exam on Wednesday. I'll answer questions yeah, answer any questions, go over the material briefly, and then that'll be it for Wednesday. Okay, quiz 4 was... Okay, so sorry, quiz 4 started out by asking, assume 4 tasks with execution time and period values of 4:15, 5:20, 6:25, and 7:30. So in each of those tuples, the first number is the execution time, or technically the worst case execution time, and the second number is the period as well as the deadline for each task. What is the utilization? If you remember, the utilization is just you just take the execution time and divide it by the period for each task and then add all those values up. So in this case, it would be 4/15 plus 5/20 plus 6/25 plus 7/30 is just happens to be 99%. Okay, the second question is assume 4 tasks with execution time period values of, oh, the same 4, right? Yeah, same 4, sorry. What is the RMS bound? So this question could have been worded a little better. I assume everyone knew what I was talking about here. So a bound is a value that defines an upper or a lower limit for something. What I'm referring to here is the RMS schedulability test, which is a value you calculate by taking the execution time divided by the period and then adding 1 for each of the tasks and then multiplying those values together, and then that's the value you calculate, and so that's what I'm asking you to find here. And then that value, if that value is less than or equal to 2, it guarantees that you can schedule the tasks with RMS without violating any of the deadlines. If the value is greater than 2, it doesn't mean that you can't schedule them with RMS. It just means that there's no guarantees that you can schedule them with RMS. And so you might think, well, I mean, if it's, then what do you do? There's not much you can do. I mean, you can simulate, you can try to schedule them, but then the question is, how long do you have to simulate for before you decide whether you can do it or not? Well, I think I mentioned that you can, like the least common multiple of the periods would work, but that could be a large value. Anyway, so what I was asking here was what's the value, and in this case, I'm asking you to say to compute 1 plus 4/15 times 1 plus 5/20 times 1 plus 6/25 times 1 plus 7/30, and the value there is 2.42, which is obviously not less than or equal to 2. Assume 3 tasks, this is question 3, assume 3 tasks with execution time period values of 2:10, 7:20, and 25:40, so these are different ones now, different tasks. Are they schedulable with RMS? Well, if you calculate, well, what I called the RMS bound, but actually what I meant is if you calculate the value that you need to do the RMS schedulability test, whatever you want to call that number, which is 1 plus 2/10 times 1 plus 7/20 times 1 plus 25/40, you get 2.63, which means it's probably not schedulable with RMS. However, that wasn't one of the options. That wasn't one of the multiple choice options. So you might be thinking, oh, is this a bug? Is this a mistake? Well, no, because if you calculate the utilization of these tasks, which would be 2/10 plus 7/20 plus 25/40, you get 117.5%, which means that it's not schedulable with EDF, meaning that it's not schedulable with anything, at least not on one processor. I didn't say one processor, but that was implied. So if it's not schedulable with EDF, then it certainly is not schedulable with RMS. So the answer to this would be no. But the no doesn't come only from the fact that the RMS value, the RMS schedulability value was 2.63. It also came from the fact that utilization was above 100%. And those are the two pieces of information you need to tell that this is not schedulable with RMS. Well, actually, you could have just calculated the utilization. That alone would have been good enough technically, because it's 117% utilization. Okay, next question. Assume 4 tasks 1, 2, 3, 4 with execution time period values of 2, 5, 4, 7, 3, 11, and 4, 12. So yet again, it's a new set of tasks. But this time you have 2 processors. Are they schedulable using partitioned RMS scheduling? If so, which task processor assignment is schedulable? Notice I said partitioned as opposed to global. So with partitioned scheduling, you basically have to decide which tasks are on which processor, and then you just do regular RMS scheduling. So in this case, there are 2 to the 4th power ways to assign these tasks to 2 processors. However, this is actually not really true, because 2 to the 4th is 16, but in fact, there's actually only 8 ways, because if, for example, you schedule task 1 on processor 1 and then the other tasks on processor 2, okay, then, or you schedule task 1 on processor 2 and the other tasks on processor 1, that's equivalent, right? I mean, so there are redundant mappings, which are kind of like the mirror image, like if you just take the 2 processors and swap them, obviously, that doesn't make an important distinction. So actually, there's only 8 ways. It's actually 2 to the 4th divided by 2. So here are all the ways you can. I tried to enumerate all of these guys. So for instance, you can assign tasks 1, 2, 3, 4 all to processor 1. And then you calculate the RMS bound. Again, it's the RMS schedulability test value. And it's 3.73, so that's awfully high. We're just going to assume that means you can't schedule, or just for the time being, we'll assume that, because we're looking to see if there's any of these that are guaranteed to be schedulable. Now, in that case, we don't really care about what's on processor 2. Of course, obviously, no task would be on processor 2 in this case, but we don't really care because we're going to write that assignment off because of the high value there that we calculated. And then we can put tasks 1, 2, and 3 on processor 1. We calculate the RMS value as 2.8, or 1, 2, and 4 gives you 2.93, 1, 3, and 4 gives you 2.37, 2, 3, 4 gives you 2.63, and 1 and 2 gives you 2.2. So basically, if you take all four tasks and put them on one processor, that doesn't look so good. And if you put even if you just put 3 tasks, there's 4 different ways that you can assign 3 tasks to a single processor, and all of those have an RMS schedulability value that is greater than 2. So those don't look so good. Now, what about if you put 2 tasks on one processor and 2 tasks on the other processor? Well, if you put task 1 and 2 on one processor, you get a RMS schedulability value of 2.2. But if you put tasks 1 and 3 on processor 1, your RMS schedulability value is 1.78, which means that you can schedule those. But now you have to also test if the other 2 tasks, 2 and 4, can be scheduled together on the other processor, which you get a 2.1 for your schedulability test for that, which isn't so good. However, if you put task 1 and 4 on one processor and 2 and 3 on the other processor, you get RMS schedulability values of 1.87 and 2.00, both of which check out. So based on that alone, I have at least one combination, one mapping that will be guaranteed to be schedulable, which is good. And then 2 and 3 on processor 1 is kind of a redundant duplicate one because because I had previously looked at putting 1 and 4. Actually, 2 and 3 on processor 1 is really just the one that I already evaluated, except it was on processor 2. So that's a duplicate. Likewise, 2 and 4 was the same as number 7, just switch the processor. So that kind of shows that there's eight possibilities. So what is the point of this? Well, the point is that in order to do partitioned scheduling, you pretty much have to fully enumerate all the ways to map tasks to processors and then evaluate your schedulability test, which is no fun at all. But that's the problem with partition scheduling. Okay, assume anyway, the answer there is yes. It is possible, and I can guarantee that 1 and 4 on one processor and 2 and 3 on the other processor will work out. Okay, assume 3 tasks, 310, 411, and 412. Under which algorithms are they schedulable? Well, let's see. The utilization there is 0.997, so that doesn't look too good. That's awfully high. That's awfully close to 100%. But as long as it's less than or equal to 100%, then it's schedulable with EDF. If we calculate the RMS schedulability value is 2.36, it's probably not schedulable with RMS. So I think that was the answer. Assume 4 tasks, 319, 420, 521, and N22. What's the largest value of N that would make the tasks schedulable with rate monotonic first fit scheduling on 2 processors? Okay, so this one, the rate monotonic first fit has a test, a schedulability test, and again, it's one of those things that says it's a sufficiency test. So sufficiency test, sufficient conditions test, meaning that if the test succeeds, it guarantees that they are schedulable. If the test fails, it's unclear. So the test is that you add up you calculate the utilization, which means that you add up the ratios of execution time to period. So 3 over 19 plus 4 over 20 plus 5 over 21 plus n over 22, and that has to be less than or equal to 2 meaning the number of processors in this case, times the square root of 2 minus 1, which is about 4.1. So that value on the right-hand side of the inequality is about 0.82, right, for 2 processors. And so we need to solve for n. Now, I don't think it's not stated explicitly, but if you look at the possible answers, all of the possible answers are integer values for runtime. So we're looking for an integer here. So if we calculate those first 3 ratios, we get 0.5960, and then we add that to n over 22, and that has to be less than or equal to 0.8284. Subtract 0.5960 from both sides of the equation, we get n over 22 is less than or equal to 0.2324, and so n has to be less than or equal to 5.11, and since we're looking for an integer here, the answer is 5. So if n is 5 or less, then we can schedule on 2 processors with rate monotonic first fit scheduling. Okay, so now we have another task set, 2.8, 5.12, 6.16, and 7.20. Are they schedulable with EDF on 2 processors? Okay, this is that really weird test that has 2 parts to it. The first part is that the utilization must be less than 2 in this case, because there's 2 processors. So 2.8 plus 5.12 plus 6.16 plus 7.20 is 1.39, so that checks out. And condition 2 is that one where you have to calculate the greatest common divisor of the periods, which is 4, if I did this right. Greatest common divisor of 8, 12, 16, and 20 is 4. And then you take 4 and you multiply it by each one of the ratios to see if the result is an integer. Now in this case, that test actually fails even multiplying it by the first ratio. So if we take 4, just multiply it by 8/12, which is the 8/12. Did I do that wrong? I did that wrong. Yeah, sorry. Where did I get 8/12 from? It should be 2 8s, actually. So that one actually works out, doesn't it? Yeah, so 4 times, or that's just 1 actually, right? 4 times 2, 8, yeah. So that one works out, right? So that would be 1. And then 4 times 5 twelfths. That's 20 twelfths. So that doesn't work out. That's going to be 20 twelfths. So 20 twelfths equals 10 sixths, 5 thirds, right? Yeah. So yeah, that doesn't work out. Sorry. So the answer is still the same. We can't guarantee schedulability here. Sorry about that. Okay. Yeah. So that one can't guarantee schedulability there with EDF. Okay. How many possible ways can 5 non-periodic tasks be scheduled, assuming they are all ready? Basically, just 5 factorial, because you have that many ways to. If they're all ready, that's the number of ways you can schedule them. Ready meaning that they're not asleep, they're ready to go, and they want to run. So you have to decide what order you want to run them in. Okay, sorry. And then which statement is true? RMS requires static priority, RMS requires dynamic priority, EDF and RMS require static priority, EDF requires static priority. The answer is RMS requires static priority. This is the reason why we are talking about RMS, because of the fact that it has static priority. In other words, every task has a fixed priority that doesn't change over time. EDF has a dynamic priority, which I can't say that I've ever built a real-time scheduler with dynamic priority. I've built real-time schedulers before, but I used RMS. I've never done one with dynamic priority. I did code up those examples though that generate the waveforms that I used in lecture, and those ones used EDF, and I found that to be, it was pretty tough even with the small toy problems. So, but the word on the street is that EDF is impractical to implement, and so RMS is generally the best, kind of the state of the art for real-time periodic scheduling because of its static priority. Okay, and then I think his last question, which statement is true? Any task set that can be scheduled with RMS can be scheduled with EDF, single processor. Any task that can be scheduled with EDF can be scheduled with RMS. Any task set having a utilization that meets the EDF bound will also meet the RMS bound, and any task set that can be scheduled on 2 processors can be scheduled on 1 processor. Well, the answer here is the first one. Any task that can be scheduled with RMS can be scheduled with EDF, because EDF allows you to go up to 100% utilization on the processor, and RMS does not. You can have task set that are less than 100% utilization, but cannot be scheduled with RMS. Just because of the fact that they have static priority. There's no way to do it with static priority, or if there is, no one's found an algorithm yet to solve that problem. Yeah, so obviously the second one isn't true, because I just said you can do EDF schedules that can't be done with RMS. And then EDF bounds, any having utilization that meets the EDF bound will also meet the RMS bound. That's wrong. The RMS bound is different. Any task set that can be scheduled on 2 processors can be scheduled on 1. Well, that doesn't make any sense at all. Although the question was that one is kind of vague, because I didn't say which algorithm. Okay, so that's quiz 4. The exam will have similar questions as the quizzes, just like the last exam. That also goes for quiz 5. So the exam on Monday will look a lot like quiz 4 and quiz 5, and I'll go over quiz 5 on Monday, or sorry, on Wednesday, this Wednesday. Okay, so back to queuing theory. Okay, so let's see, where were we with queuing theory? So talked about how queuing theory. What is queuing theory all about? It's really just kind of a it's really kind of hard to define, because it's really just a it's sort of a methodology to analyze queuing systems. It doesn't really necessarily give you the answers you want right off the shelf, depending on, now there are some sort of pre-canned queuing models that have pre-made solutions for you, like the MM1 queues that we're studying in this class. But if you come up with some really crazy queuing system, complex queuing system, you can't necessarily just look up the solutions. You might have to actually figure it out and derive the solutions on your own. And when I say solutions, what I mean is an equation to give you the waiting time, the number of customers that accumulate, and the idle time of servers, which are the three main things you want to know. And there's other information you can get as well. But depending on the complexity of the queuing system, you may have to just kind of follow the tenets of queuing theory to figure out how to calculate these values. On the other hand, if you just have an MM1 queue, you can just kind of pull these equations off the shelf. And in this lecture, I'm going to derive them for you so you can see how they're derived. And that's really the point of queuing theory, is to understand how you derive these equations more so than just giving you the equations. So that's kind of the subtlety here behind queuing theory, is that it's really kind of a methodology that's kind of just rooted in statistics, which is why this class is a prerequisite of Stat 509. Okay, so queuing theories have queuing systems rather have characteristics. So a queuing system is the combination of a queue or queues and the servers. So again, the queuing system combines the queue and the servers as a box, as a module, and then you have customers come in and then they are serviced. So they have a probability distribution for arrivals and a probability distribution for services. Service times. Those don't have to be the same. In this class, they're generally stochastic, meaning that they're random variables. And then there's some other subtleties. You can have single or simultaneous arrivals, and it can be stationary or non-stationary. You can have customers that will leave if the queue is too long, which is, of course, the way that it's kind of a more realistic scenario when you're talking about human queues, not necessarily the case so much with electronic queues. And then there's the service pattern, and that's how long it takes to service. And the number of servers and service channels is a parameter. These are all parameters for the queuing system. Now, as I mentioned, you might think, if you think about it, or at least the way I think about it, or at least the way I thought about it before I revisited this stuff, if you can get customers out faster than they're coming in, you would think that this would be an easy problem, right? And if you can't get customers out as fast as they're coming in, then you're just going to have a continuous buildup, right? You're just going to have an infinitely long buildup, right? And that's really the simplest way to think about it. But in reality, it's required that you be able to service customers as fast as they come in. But because of the stochastic nature of the arrivals and the service times, you end up getting lines even when your rate of service is greater than the rate of arrivals. That doesn't seem, to me at least, maybe that's obvious to you guys, but to me that was kind of mind-blowing. It's like, yeah, you're going to get a line, and not only you're going to get a line, but you're going to get a you're going to reach an equilibrium where the line will sort of build to a certain length and kind of stay there, generally speaking. I mean, it'll fluctuate, but there'll be an average you can calculate for the line size just based on the service pattern and the arrival pattern. To me, like I said, that to me, kind of blows my mind. That's crazy. So queues are denoted as five parameters. First two are the arrival and service time distributions. There's little abbreviations for those: exponential, general, deterministic, Erlang, mixture of exponentials and phase. Number of parallel servers is the third option, and then you have the fourth is system capacity, and the fifth is the queue discipline. If the system capacity is infinite and the queue is first come first serve, then you can omit those. So, for example, we're talking about MM1 queues, which are exponential arrival and service time, and one parallel servers. the simplest type of Q system that you can come up with. I talked about Little's law, which is a very simple law that says L equals lambda W, where L is the average number of customers in the system, lambda is the arrival rate, and W is the average time in the system. Notice that we have an arrival rate here, but we don't have a service rate. Well, what's up with that? I mean, that's problematic. Well, the reason we don't have that is because that parameter is kind of absorbed as part of W, which is the average time in the system. So this is a very abstract rule that defines a value called W, which is an abstract way to calculate, the waiting time as a function of the arrival and the service time distribution. So obviously Little's law, for that reason, Little's law is not the end-all and be-all solution of queuing theory. It's just kind of the last step that you typically will calculate when you're deriving equations for a given queuing system. Okay, so then let's see, exponential distribution. I hope you guys are comfortable with this from Stat 509. This is pretty much the most simple random number distribution there is. It's even simpler really than a normal distribution because there's only one parameter, which is lambda. It's the arrival rate. Lambda is literally just events per second or events per whatever unit time that you're in, and 1 over lambda is the mean, is the average for the whole distribution, which is pretty convenient. 1 over lambda squared is the variance. And so that's kind of interesting in and of itself, because what that means is that if you decrease lambda, then the variance shoots up like crazy, which is indicated there on that plot, because if lambda is 1.2, it's basically a very flat distribution, which is indicating that the variance is very high. So if you crank up lambda, you get I was opposite. Sorry, I said that wrong. If you crank down lambda, for lower values of lambda, you have higher variance because, again, it's lambda's in the denominator and the variance. So lower values of lambda give you higher variance, and so lower values of lambda give you kind of more spread. You get more unpredictability in your inter-arrival times. The random variable, itself represents the time in between arrivals. And then we have a PDF, CDF, and CCDF, which are equations that just tell you, that give you information about a given a proposed value of the random variable. So for example, the CDF, if you have a proposed value, say 4, then you can plug that in and you'll have the probability that the value is going to be less than 4. Right, so you can use the CDF to know if the value, or if the random value is going to be less than or equal to a certain value. In other words, and then the CCDF is the opposite. It's if the probability that the random value is greater than the value that you give it. So in this case, T is the random value, and uppercase T is the random value. Lowercase t is the value that you're evaluating at. You're evaluating the distribution at. And keep in mind the probability density function is a relative and not an absolute probability, because this is a continuous probability distribution. Okay, so then we had some examples here. I went through, I'll skip over that unless anyone has a question. Then there was this thing, we start getting into some of the rules of the exponential distribution. If you've got n independent exponential random variables with n different rates, then if you add up the rates and you reevaluate that as its own random variable, that represents the minimum. It's a random variable that represents the minimum of the original values of the original random variables, t sub 1 to t sub n. I mentioned last time that this can be confusing. I almost fell into this trap because if you add, this is not the same as adding two exponential random variables. This is not correct if you're adding them. What this is giving you is the another random variable that is the minimum of this original set of random variables. So don't fall into that trap. If you add, I mentioned if you add Gaussian random variables, then you can just add their means and basically add their variances. But that is not the case for these exponential random variables. Okay, so I had an example. Assume 10 exponential random variables, t1 through tn, all with rate lambda equals 0.01. What's the probability that the minimum of these will be less than or equal to 2? And then so basically you calculate that based on a random a lambda of 10 times 0.01. So the answer turns out to be 86%. Now the probability of any one of those being less than or equal to 2 is only 2%. So you have 10 random variables. The probability that any one that a specific one of those will be less than 2 is really small. But the probability that the minimum of all those of 10 of those guys being less than 2 is 86%. So to me, that seems like a huge difference. That's a big difference, you know, 2% for one versus 86% for all 10 of them together. So here was an example of that. Time until a bus arrives is exponential with mean 20 minutes. The time a taxi arrives is exponential with a mean of 5. Notice that I'm trying to trick you here by giving you the mean and not the lambda. So in order to get the lambda, you have to take the reciprocal of the mean. What's the probability of waiting at least 5 minutes for a bus or taxi? So you add together the two lambdas, which is 1 over 20 plus 1 over 5 is 1 over 4, and then calculate the CCDF, the complementary cumulative distribution. And that would be 29%. Okay, and then there was a Poisson process, which is the probability of n events occurring by time t. The Poisson process, I don't really, it's funny, it's really just a variation on the exponential distribution, but they call it a process because it's counting values. Yeah, so that's basically the idea, but again, you're just kind of just plugging numbers in. So you've got a lambda and a t, as we did before. So lambda is the rate and t is the time. But then you've got n, and n is the number of events. So for example, what's the probability that 2 events occur in the time frame 0 to 3? Would just be you plug in 3 for t and 2 for n, and plug in the lambda, and you get a number. Okay, right, and then we talked about splitting and superposition, which these are pretty easy. Splitting, if you split a Poisson process and each of the different outcomes are weighted with a oh, sorry. Wait a minute. Let n of t be a Poisson process with rate lambda. Suppose that each event is labeled an I-type event with probability, yeah, p of I. So you're weighting each of the types of events that are split off of the original one. And so basically, each one of the split processes would basically have its rate modified by p of I, which is the probability of that. So there's a question on the quiz about this that that basically says that if you have people arriving at an airport and then they kind of split off into different lines, security lines, then that's kind of what this is. It's kind of the idea where you have one flow coming in and then you're splitting it amongst different categories. Now they have to be random. You can't, they have to be independent, which means that the determination of which event is assigned to whatever process has to be randomized according to a specific probability, p of I in this case. And then superposition is kind of the opposite of that, where you have you're combining together multiple Poisson processes, and that just basically, in that case, you're adding the rates together. Okay, okay, and then I think this is about where we ended up last time. So we were talking about a birth-death process. I mentioned that this is an example of a Markov chain. A Markov chain is a state machine, And the important thing to understand about that is that you can basically, the system can be in one state at any one time. So you've got states, and then you have rules as to, if you're in a state, what other states can you transition to? And in a birth-death process, it's very restricted because you can only transition, each state only has 2 outgoing transitions except for state 0, where one of the transitions is adding a customer to the system, and the other transition is servicing a customer, and so you're losing a customer in the system. And in a Markov chain, instead of a traditional state machine where you have an input that causes you to transition from one state to another, in a Markov chain it happens just randomly. You just randomly switch states. But the time that the time in which you have to wait to make that random switch is governed by an exponential distribution. So each state's outgoing transitions will have a rate associated with it. And in this case, all of the rates that go up one state number is lambda, and all the states that go down one state number is mu, because lambda is the arrival rate of customers and mu is the service rate of customers. And they're all the same. So, for example, it doesn't matter what state you're in, it's always lambda and mu that represent your outgoing transition rates. Now, I mentioned at the beginning of the lecture, I mentioned that your service rate has to be greater than or equal to your arrival rate, or you're in trouble. So the ratio of lambda over mu must be basically between 0 and 1. In fact, I think it's generally less than 1 and greater than 0, so non-inclusive. So keep that in mind, because if that's not true, then a lot of the theory with MM1 queues falls apart. So the time that you spend in an individual state is an exponential random with rate lambda plus mu, which is kind of an example of the splitting process, right? Now you might say, wait a second, splitting was a property of Poisson processors, not of exponential distributions. But yeah, it applies here as well. So if that's, again, the split in the sense that an event happens, it can be an increment or a decrement, and so the rate at whichever one of those happening would be lambda over mu. Actually, it's more. It's actually more of an example of the minimum. The minimum of random exponential random variables. It's more accurate. Okay, so what we want to do is calculate P of n, which is the probability of being in state n. If we know P sub n, then we can use those probabilities to calculate a weighted average. So, for example, if you have, if you add up nPn for all the states for n, starting at 0 and going to infinity, that's going to give you a weighted average of state number, multiply each state number by its probability. And that's going to give you the number of expected customers in the system, because n is the number of customers in the system. I'm not sure if I should have emphasized that more. But if you're in state 0, it means there's no customers in the system. If you're in state 1, it means there's one customer in the system. Now, if there's one customer in the system, that customer is probably going to be getting, serviced, right? Meaning that it's not in the queue, it's being serviced. If you have 2 customers in the system, if you're in the state 2 and you just have one server, then that means there's one customer in the queue and one customer in being serviced, right? That's assuming there's one server, and we're assuming one server because we're doing MM1 queues. So that's what the states represent. It's just the number of pending requests, essentially, or pending customers. Okay, so the idea with analyzing the system is flow balance, and this is to be honest with you, I think this is kind of not entirely intuitive, But in steady state, the rate of transitions out of a state must equal the rate of transitions into a state. So that means that lambda plus mu multiplied by the probability of state n has to balance. So remember, lambda plus mu is the amount of the rate at which the rate of the exponential variable that defines how long you stay in state Pn. And then if you take lambda, multiply that by Pn minus 1, that represents coming in or adding a customer from state n plus 1, plus mu, which is the probability of servicing a customer from state n plus 1. And then that applies for every state except for 0. And with state 0, you just have one outgoing and one incoming transition, which makes sense. Basically, lambda P0 equals lambda mu P1. So you can either go up, you can add a customer from 0, or you can service a customer from state 1, and that should be equal. Okay, so that part, see, to me that seems, I don't know. I think that's kind of counterintuitive, but that's where the queuing theory is built on this notion of balance, right? This flow balance. Okay, so we need to derive some things now. Ultimately, again, we want to know waiting time and number of customers, and idle time of servers would be nice too. So idle time would just be simply, probability of being in state 0, right? So that's all we need to know for that. Waiting time is waiting time we get at the end, right, with Little's law. And the number of customers that may accumulate in the system is calculated the way I just explained, which is basically just a weighted average of n of all the n times pn's, right? It's a weighted average. So you take the probability of being in each state and you multiply that against the actual number of customers that state represents, and then you just add them all up, and that's going to give you the expected number of customers, or the average number of customers. Basically just calculating a weighted average where the weights are the probabilities of being in every state. Those probabilities are just simply a function of lambda and mu. That's it. That's actually not that complicated, although it's kind of complicated to get to that point. So we will do that now. So we start with the flow balance equation, which is what I just gave you, and then just rewrite it where we're going to put p n plus 1 on one side of the equation. So make that a function of p of n and p of n minus 1. So this is this isn't very helpful. Ultimately, what we want is the probability of being in a state that ultimately should just be a function of lambda and mu. That's what we want, right? But that's not what we have. We have something that we've got 3 different probabilities, and they're relative to n. This is no good, right? I want to know what the probability of being in a given state is as a function of lambda and mu. That's what I want to know. So to get there, we first of all start out with the equation that we just had, but we're going to just plug in 1 for n. So we're going to build this up recursively, or no, incrementally. All right. No, we're going to do induction. Yeah, that's it. We're going to build it up inductively. So we're going to set n to 1. So we have p sub 2 equals lambda plus mu over mu p1 minus lambda over mu p0. And again, that's just from having just done the flow balance equation, rewriting it as a function of p n plus 1, and setting n to 1. That's it. Then we go back and we observe that that flow balance equation thingy that had to do with state 0 and 1, the special case, we can rewrite that as p1 equals lambda over mu p0, and just substitute that in to the equation on the left, and multiply everything out, do some algebra, do lots of algebra, not a lot, but yeah, a little bit of algebra, and we get p2 as a function of p0, because basically we're able to substitute lambda over mu p0 for p1. And by doing that, we now have, well, we just have 2 probabilities now instead of 3. So that's a little better, but we still don't know what the probability of being in state 0 is. So, you know, we still have an issue with that. What happens then if we continue doing this, though? So we set n equal to 2. So now we have p3 equals lambda plus mu over mu p2 minus lambda over mu p1. And now we have the p1 and p2 values as a function of p0 from the last slide. And we substitute in both of those, right? So basically we get rid of p2 and we get rid of p1. And so now we'll have what we'll get is an equation p3 relative to, or as a function of p0, right? And so we do that, and we end up with p3 equals lambda 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 divided by mu 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 p0. And so this just continues, and you can then generalize this as the probability of being in state n is simply lambda over mu to the nth power times p0. Okay, well that's better, that's nicer, except it still doesn't get us what we want. I want to know, I want to give me a state number, and I want to know the probability of that just as a function of lambda and mu. We still have this issue with this equation because there's a p0 in it, and I don't know what p0 is. Okay, so we got to figure that out. So to do that, you can say if you add up all the probabilities of all the states, it should add up to 1. Now, remember, though, there's an infinite number of states, so because the system capacity is infinite, remember? That's why we have MM1 and not, we don't have a fourth value after MM1. So, right, so 1 equals the sum of Pn from n equals 0 to infinity, and we now know the probability of Pn. We can substitute that in. Again, it's not perfect because there's a p0 in there, but we can replace p sub n with p sub 0 times lambda over mu to the nth power. So that's a little better. Okay, so now we're going to set lambda over mu to be a new variable called rho. You don't have to do this. This is just to simplify the math a little bit. But rho is just the lambda over mu, the ratio of arrival over service distribution rates. And, you know, obviously this is 0 and between 0 and 1, as I mentioned. So then you can replace lambda over mu with a rho. So, oh, and you can move the p sub 0 outside the summation. Okay. Okay, so so now this next step I mentioned is kind of a basic mathematical rule. If you add up a bunch of numbers from 0 to infinity, where the numbers are, you know, some value to the nth power, as long as rho, in this case, the base, is less than 1, right? It has to be less than 1. Can't be. Even 1 wouldn't work here, right? Because if you put 1 in for rho, you get infinity here. So you got to be less than 1. And obviously 0 would just give you 0, so greater than 0. So if rho is greater than 0 and less than 1, then this summation is equivalent to 1 over 1 minus rho. And I gave an example of that last time. It works out. You can plug different values in. It just works. So this step is a little, I mean, it looks arbitrary. You're like, I don't, you know, what is this all about? It's just a thing, right? It works. Okay, so we have that thing, and we can then replace that summation 1 over 1 minus rho, the equivalent of that summation, 1 over 1 minus rho. We can just drop that in place of the summation there. So now we have 1 equals p sub 0 times 1 over 1 minus rho. And oh my gosh, check this out. We now have what appears to be a solution for P sub 0. P sub 0 is 1 minus rho. That's it. Oh, good. Well, that's good. All right, well, we know the probability of the system being empty as a function of lambda and mu, so that's nice. That turned out to be pretty simple. Okay, so the problem is that we need P sub n. So we still need to know the probability of being in state, I don't know, 7, for instance. So we can go in and replace, remember we had basically P sub n was P sub 0 times lambda over mu to the nth power, right? Lambda over mu is rho, so we can drop rho in. And now that we know P sub 0, well, we can substitute that in. So P sub 0 is 1 minus rho, and we can multiply that by rho to the nth power, and that gives us the probability of being in state n. Well, that's awesome. Well, there you go. That gives you the probability of being in a state. That's good. That's good progress, right? And that'll give me a lambda and mu, and I'll tell you the probability of having in any number of customers you want. Pick an n, and I'll give you the probability. Okay, so now the problem is we need to know what is the expected number of customers in the system. So for this, like I was mentioning earlier, you can calculate, if you know P sub n, which we do now, we can just multiply that against n, which is really just giving us like a weighted average. It's like saying, well, there's a 25% chance of being 1 and a 50% chance being in 2 and a 25% chance being in 3. So you just multiply, 0.25 times 1 plus 0.5 times 2 plus 0.25 times 3, and that gives you like a weighted average, right? So that's all we're doing here. And so by using the probabilities as weights, we can, get an expected value, an expected number in the line or in the system. And then the line is also, we can also get that as well. So we can take, we can do some modifications here. We know P of n is 1 minus rho times P of n. So we can take we can substitute in the P of n in there and replace it with 1 minus rho times rho of n. Sorry, I think I said P. See, I got tripped up by the rho and the P thing. P sub n is 1 minus rho times rho of n. So we can substitute that in for P of n, and that gives you could take the 1 minus rho and take that outside the summation. So now we have 1 minus rho times the sum from 0 to infinity of n times rho to the nth power. And again, n is just weighted, is used for the weighting of the number of customers in there. Okay, so now things get a little crazy. And the reason is we have to get that summation out of there. That's the problem. How do you get the summation out of this thing? Well, before we were able to get the summation out because we had it in that, had it in a certain form. And so we kind of do, because we have the summation n equals 0 to infinity rho of n. That's what we had before. But we can't use that trick because that other n multiplier. That's the problem, is that we got that n. We got that extra n in there, and that makes it so we don't have a convenient way to just dump this into a use that mathematical trick. We just can't do that this time, not directly. So you use this other thing where, and this part is a little weird, but if you take the summation and you expand it out, right, what you're really doing is saying the summation is rho. Well, actually, if n is 0, this whole thing is 0, right? So we skip 0, right? When we start at 0, n equals 0, then n times rho of n is 0. But when n is 1, we get rho, right? And when n is 2, it's 2 rho squared. And when rho is 3, it's 3 rho cubed plus 4 rho to the 4th power, and so on. You can factor rho out right? Because these all have rho in it. All of these terms in this summation have rho. So you can factor a rho out, and then you can rewrite the summation as rho. Rho is not a function of n, so you can factor out the rho. Rho's like a constant. And then you can change the summation to start at 1. And then basically you want to come up with the summation that's equivalent to 1 plus 2 rho plus 3 rho squared plus 4 rho cubed. So obviously it's going to be, you're going to start with n, right? Because there's 1, 2, 3, 4, right? But then the power of rho is 0, 1, 2, 3. So the power of rho is going to be n minus 1. So it's going to be n times rho n minus 1. And we're going to start this summation off at 1. Okay? So basically, these are equivalent. We just use the trick. You know, we factor out a rho, basically. Okay, so now, and this is the weirdest part. It's just hang with me here for a minute. This part is kind of crazy. So it turns out that this summation is the derivative of that other value of that other summation, n equals 1 to infinity rho of n. Remember that one? That was the one we used the trick for. Now you might say, wait a second, wait, time out. I see what you're doing here. This is a trick because when we did this last time, n was started at 0, didn't it? Did it? Oh yeah, it did. Look, n started at 0. So before we had this summation n equals 0 to infinity rho of n. And we found out that this actually is the same as saying 1 over 1 minus rho, right? But n started at 0 here, right? Now, I'm trying to pull a fast one on you here, right? I put a 1 in there, right? So this is the derivative of that, but that is not the same thing as we had before. True, but guess what? There's another mathematical trick. Turns out that the summation of rho to the n from n equal 1 to infinity is rho over 1 minus rho. Now that's not the same as what we had before. Remember, before we had 1 over 1 minus rho. So basically, if you start n at 0, this summation breaks down or is equivalent to 1 over 1 minus rho, right? But if you have this other summation that's very similar, except it starts at n equal 1, you get a similar thing, except a little bit different. It's rho over 1 minus rho. So this, again, this is just a mathematical thing. You can put numbers in here if you don't believe me. As long as rho is between 0 and 1, this will hold. Okay? Okay, so now, okay, so what do we have here? We have the fact that we have this thing, right, which we calculated from here. And we also know that this is the derivative of something else, which we haven't even looked at yet, but this something else happens to break down into this nice form, right? So now we can take this, and we know that is the derivative of that special mathematical thing, rho over 1 minus rho, which is the other thing that we just came up with. So we found a summation that's the derivative of another summation that breaks down into this nice form. And you might say, what in the heck? Who cares? Why would you do that? Well, it's because I can then take the derivative of rho over 1 minus rho and get 1 over 1 minus rho squared. So in other words, what I've basically done is I found a way to eliminate the summation. I got rid of this infinite summation by doing basically 3 tricks, right? The first trick was factor out rho from the first summation was pretty straightforward, right? This was a weighted average. From the weighted average, I expanded it out. I factored out rho. Then I observed that thing that I had after having factored out rho, or at least part of it, right? Because actually it's part of it technically, because that rho, notice I took that first leading rho out. So I took that first leading rho out, but what was left over was this other summation, which happened to be the derivative of another summation, and that other summation had a nice form that I could use to get rid of the derivative. But I couldn't just get rid of the derivative right away. I had to then say, well, I got to take the derivative of that special form, which, and to be honest, I didn't remember how to do this in calculus. How do you take the derivative of rho over 1 minus rho with respect to rho? Well, you have to do it by parts. I guess, right? But what you end up with is 1 over 1 minus rho squared. Okay, so that's basically that, and that on the left is essentially our weighted average without the leading row. Okay, so now I can take, I can basically take what I've got, which is the 1 over, let's see, the 1 over 1 minus rho squared. I have to plug back in the original row. So that was the one I factored out, sorry. And then I have to multiply it by this first leading row, 1 minus rho here from this, which again I got just from the weighted average equation. And I solve for that, and I can eventually just get it to rho over 1 minus rho, or if you re-express rho in terms of lambda over mu, it's lambda over mu minus lambda. Okay, so I know that was that's a lot of steps. But the bottom line is that now I have a solution for L. You might say, what the heck is L? Remember L came from Little's law? L was the number of customers? L, length, I guess? Is that what it stands for? Length, number of customers, the expected N. What's N? Well, N's the process. Okay, L is the number of customers in the system, and it is rho over 1 minus rho. And so basically I showed you how to get there, you know, how it was derived. But the point is now we have an equation for it. Okay, so let's take a look at some examples here then. I generated this plot in MATLAB because I was kind of curious if, let's say that your mu is 1. Mu is your completion rate. That makes sense, right? 1 customer per second, say. Or 1 customer per hour, I don't know, 1 customer per minute, I don't know, whatever your time unit is, right? That's your mu, right? And now I can hold that as a constant, and I can take the arrival rate, which is lambda, and I can start to scale that guy up. Now, obviously, I can't get to 1 because that would be trouble. But I can scale it up, you know, up until I kind of brush up against 1. And check this out. Number of system, look at that. As lambda gets to about, you know, 0.85, I already have 10 customers in the line. But then if I keep increasing lambda, you know, it just shoots straight up really fast. Now, you might say, you know, weird thing is that, you know, keep in mind that all the values of lambda I'm showing here are less than mu, meaning that my rate of arrivals is less than the rate of completions. But even so, as I get closer, that number of people or customers or requests or whatever that are in the system increases, you know, quite dramatically. Okay, so how about the number just in the queue? I don't care about the whole. See, the problem with the queuing system is the queuing system includes the queue and the servers. What about just the queue? Because I might want to know that to adjust my queue size. Well, that is, I'm going to note that as NLQ, L sub q, which is the expected value of N sub q. And so this is really just the summation of N equals 1 to infinity. And this is another weighted average, except notice in this case, the value I multiply against the probabilities is N minus 1 because I'm assuming that 1 customer is always being serviced. And so you have to have more than whatever N minus 1 is the number that's in the queue, right? So that's why I'm weighting P sub N times N minus 1. And so this guy you can break apart. This summation you can break into 2 summations. You can distribute, you know, P sub N. And then check it out. This first guy, we already know the solution to that, right? And so that's L, right? L. This first term is L. You know, we're calculating L sub Q. We already know L, so we can substitute this for L. And then this one's easy because this is basically just the probability, all the probabilities added up, except for probability 0, right? Well, we know all the probabilities added are 1, so 1 minus P0 is the equivalent to this, you know, summing up all the probabilities from 1 to infinity. P sub 1 to P sub infinity is pretty much just 1 minus the probability of being in 0. So that's pretty simple, and we already know what P sub 0 is. We calculated that. So P sub 0 is rho, right? Yeah, P sub 0 is rho. So rho over 1 minus rho is L. We subtract 1 minus P sub 0 is rho. And then we can rewrite that as rho squared over 1 minus rho. So that's the expected number of values in the queue. So that sounds, I mean, you can just kind of regurgitate that equation, and that'll work for an MM1 queue. Well, it's not going to work for other types of queues, but it'll work for that one. And then you can also rework this if you don't want rho and you want mu and lambda, then you can also plug in mu and lambda here instead of rho. It's just a rewriting of the equation. Okay, and then finally, the last step is the waiting time. And as I mentioned earlier, I alluded to this, but once you have L and you already have lambda, well, then you just apply Little's law and you get the waiting time. So this is pretty simple. The waiting time is L over lambda, because remember, Little's law said that L equals lambda W. So you rewrite that. W equals L over lambda. And so now we know L, we know lambda. We plug those in, and you get rho over lambda times 1 over P. This is just plugging in and solving, right? And then, this is weird, right? Because we've got rho and lambda. It's kind of, typically you're either going to have rho or lambda. So you can substitute in lambda over rho you can substitute lambda over mu for rho, and you can, that ends up being just 1 over mu minus lambda. It's your waiting time. So that's it. And then you can do the same thing for just the queue, the waiting time just for the queue. And so to do this, you just use, instead of L, you use the L sub Q, which we've already calculated that. You substitute that in, and you get rho over mu minus lambda. And so I did another plot. This plot looks a lot the same, very similar to the other one, except this one plots the average waiting time versus lambda if the mu is fixed. And you can see that, same kind of thing. Basically, once those values get close, you get this really steep uptick in waiting time. Okay, do we have a... Matthew, did you have a question? Oh, waiting on what? Yeah, thank you. Good question. That's the time you're waiting. So basically, if you think of this like a barber shop, basically, you have arrivals, and so you have the rate at which people come in, and you have the rate at which the barbers can cut someone's hair. And so what you're calculating is W is the time I can expect to wait it's the time I can expect to wait to get all the way through the barber shop. So that includes the waiting in line as well as cutting my hair. W sub Q is the time I can expect just to wait in line. So if I go to a barber shop and I know the lambda value for people arriving and the lambda value for the barbers, then I can calculate how long I can expect to wait in line to get my hair cut. That's what that is. Make sense? Yeah. Now, if you calculate P sub 0, that's the probability that there will be no customers in the system. So that's basically the amount of time you can expect to have no one in the store. Okay, so here's another example. Oh, I'm almost out of time. Okay, actually, you know what? I have an example here, but I'll go through this example. I'll go through this example next lecture. If you're interested, you can check it out on the slides. And there's some similar questions in the quiz. So I'll go over the quiz on Wednesday, and I'll go over this example on Wednesday, which will kind of work together as a way to review for the exam, and then I'll go back over the real-time scheduling stuff, and I'll take any questions you have on Wednesday. If you have any other questions in the meantime, feel free to email me. And don't forget to take the exam, or sorry, the quiz before class on Wednesday. That's important because we're running up into the exam. Any other questions? Okay, great. Okay, then we'll see you on Wednesday. Thank you.